valid address. Bad coded. Yeah, you probably, well, BF. Yeah, that would land somewhere. That'd land somewhere. %N, on the other hand, unlike everything else that prints something or specifies formatting for something, nothing is printed. Number of characters written so far is written to whatever pointer is on top of the function stack. If you don't have the proper arguments pushed, as if we provided our own string rather than programmer providing the string, then whatever's on the stack, you can just keep pushing until something's on the stack that you like and that you want called. %N is the only modifier that writes, and there's that caveat one more time. Assuming you can provide the string, finding the offset means that we pop the stack so many times. Each of these pops a stack. Each of these %08x, because it pulls 8 hex digits, which is the same as one word, which is the same as one address, one pointer. So finding the offset means just doing enough pops, or using, there's another technique where you actually specify an offset. I'm not going to cover it, but it is the sexier way to do it, I guess. Only works on some OSs. Direct referencing of stack variables. So here, this is what this printed out. The brackets don't have anything to do with this format string. They actually get printed as brackets. What we end up here is A, that group of 4 A's, is printed out by that %08x. It prints 8 hex digits. The argument that it happens to pop is 4 A's. So we end up with 41, 41, 41, 41. Then we got B's, 42, 42, 42, 42. That's what we want to see. Now you are controlling what that format string is doing. Oh, right, finding detours. This is pretty important. Object dump will take an executable and print out its sections. One of those sections is detours. When you actually run this command line, you will end up with like 4 lines. One we're interested in is detour end. Here's an example where those A's were. I'm not going to print the hex characters I'm interested in writing backwards. 08, 04, 83, 48. I actually did these at different times, so never mind the fact that's not actually the address that it says we want to go to, but whatever. And what'll happen is this %N here will write this address, which was those A's, is now our hex address. We'll write to that address the number of characters we've written so far to the screen. So list in GDB will show you your code. List line number will show a specific, or centered around a specific line number. So if you do list 10, it'll show like 5 through 15 or something like that. If you have it like 20 lines large. So x/ will print whatever stored at the address you specify in GDB in the format that's specified by the second argument. So x means we're printing hex information, and since I specify a pointer, it prints out the pointer and what's stored at that pointer, actually. So we use break, and I usually use like break 1 and start stepping. When you use GCC, use the -G GDB flag to make GDB work with your executable. It's pretty important. And you'll end up, if you are at the right point, you'll end up with this line here. Also, you can use display /x $EIP, and each step it will show you what EIP is. So if you're really unsure, try writing to EIP each of those points. I mean, a lot of this stuff really comes down to how you want to solve the problem. There's no, there's right ways to do this, but you don't have to do it the right way. You can just do it for fun as a challenge. just jump in, go for it. So for instance, this line here, it's not very clear. These are 2 pops so that I end up at the beginning of my format string. And then I'm doing 4 successive writes of a byte. So 48950. So here's the first place, the most significant byte that I want to write to, which would be 2b. The reason being it's 2b is because we printed these 2 brackets after the 29, which was written by the previous address, and then the 2725, and that's why it steps down 2b, 29, 2725. B is 11 in hex, 11, 9, 7, 5, 2 apart from each other. That accommodates for the brackets. So that's what's happening there. So our shell code is at BF, FF, F313. So we print this string, which writes to our address of detours, the value BF, FF, F313. The way we do this is I use these lines, which print so many A's, to go ahead and push this over. There's better ways to do this. There's way better ways to do this. You can use %.238 D, and it will print a decimal number with 238 points after the whatever that thing's called, period point, whatever. Yeah. Decimal. It's called decimal. A decimal point. Yeah, there you go. And it'll print the number of characters you need, and not look so funky. But this is more intuitive. We're printing A's there, and it increases the number of characters written so far, so that %n is what we want it to write. So that's how we control what %n writes to the address that is on the stack, which is the beginning of our format string. Malloc and doubly linked lists. Many operations to copy data can be made to copy data to an arbitrary location. You can sort of read that. Once again, there's a lot of functions that do funny things. There's a lot of algorithms that, by nature, copy data around. If you can get in and corrupt that, let's say you don't have any convenient way to overwrite a point that gets jumped to, you don't have any convenient way to overwrite detours or EIP. There's other ways, for instance, format strings, to write to those addresses. So maybe you can only corrupt a bit. If that was for instance, luckily on x86, since it's a little endian, when you overwrite a bit, that is the bit from the least significant byte. So if it's a small number, you can decrease that number enough so that if it's an address, it suddenly falls short, and if it falls short of where it was, then it might end up where you control. So it is possible to do an exploit with 1 bit. A linked list is something that points from element to element in memory as a pointer to the next thing and a pointer to the previous thing. A doubly linked list does. When you delete one of these items, it has to copy the next pointer from the one you're deleting to the previous pointer plus the offset to the next in the struct, the address of next, and then it does the same thing with the previous address to next to the offset of the previous pointer in the next chunk. So any point where you can overwrite next and previous, it will do plenty of writes for you to where you want it to go. So this is sort of hard to read, but think of it this way. If that's 0, wherever we're starting, this is 4, 8, 12, 16. In hex, that would be 0, 4, 8, what would be CF? Yeah. So those are each parts of a struct. A struct is a collection of different kinds of variables into one thing. So in this particular instance, we have previous size, which is the size of the previous chunk in memory, size, which is the size of the current chunk in memory, previous, which is where previous is, and next, which is where shellcode is. Well, next is where the next chunk is. It puts a pointer to the next chunk. It takes a second. And then data, which is the data, what is stored in that element of the linked list. This is a sort of standalone example, since we copy to the pointer next to the point where the pointer next should be in previous. We write to we write the address of EIP minus 12. The reason being, when it does the write, it'll take the next pointer. When it writes, it'll take the address in previous and write to an offset of that to where it thinks next should be the address of our shellcode. So if it's 12, if it's 3 bytes before, no, if it's 12 bytes before EIP, that's in previous, the offset will be, the offset to next would be 12 bytes after that point, which would be EIP, and then we write previous there. So that's pretty straightforward. Here, let's say previous size, we can overwrite 1 bit. Well, if that's the least significant, part of the least significant byte, then we can change it to something lower in memory, and then we can do the same trick, except this isn't where one of our elements should have been. It might be the data segment of one of our elements, but it doesn't know that because it checked previous size. This only works in a couple situations. It depends on what the algorithm is doing. That is doing your D-link on your format string. So it's just a couple different ways of looking at it. Stack protection, canary values. When you actually start talking about trying to do this against some of the more modern stuff, what people do is, since you're trashing memory, one thing you can logically do is stick a value next to each of those critical values in memory and check it immediately after every dangerous function. And this works pretty well, except that that random value has to be somewhere else in memory. So if you can gain control of that variable pointer, you can do that. If it jumps out, then you have to get really creative to get that right, or to get it to something it will accept. For instance, in glibc, one of the things it does, I should actually go back. Yeah, one of the things it will do is check before it does any operations, size and previous size, to make sure they're more than the minimum size of a allocated chunk, which is something like, I think, maybe 12 bytes or something like that, 24 bytes. And then it will check previous size and make sure that it matches what it thinks should be at previous, or it will take previous, use prev size as a, what's up? Oh, it'll use prev size as a sort of offset, and then make sure what it finds at the next location where it should be a pointer is a pointer. What's up? No. I have mainly read about canary values. I don't really try to defeat them. It's not required for the games usually. I know have the ghetto hackers done non-executable stacks, but not canary values. So this is something that would be interesting for games, and effects if you want to write exploits.